Hi there, Jack from Smoky Mountain Scientific here. Last time I did a video I showed you how to assemble the WheeTrometer spectrometer, and today we're going to talk a little bit about getting it used. Okay, so this is a photograph of the WheeTrometer, and what we're going to talk about first is getting light focused onto the detector. What you see is the lid off. There is over on this side, this is the cell holder, and in the background you can see a cardboard box that I have over a compact fluorescent lamp. The lamp turns on and light comes through, reflects off the collimating mirror back here. Here's the grating, comes over the focusing mirror, and then ends up on the detector. I've put a little piece of white paper in there to make it possible to see the output to see the output, right? So compact fluorescent lamp has a red line, a green line, and some other lines out here, and you can see these reflected off the white piece of paper. What we need to do is to make sure that those lines end up centered over the detector, and we'll do that by adjusting these machine screws. There's one on the right hand side, there's two on the left. The one above that you can see out here, right? And what those do is they pull in the mounting that holds the focusing mirror and changes the angle of the mirror. All right, so this one out here will predominantly affect what direction, where on the spectrum the different pixels register, and the other two will determine the up and down effect of the mirror. Okay, so what we're really concerned with is getting the spectrum centered on the detector, mostly in the up and down direction, and that's we're going to talk about how we're going to adjust this briefly. That is that. Here is a picture of the output from the compact fluorescent lamp. This shows that sometimes the output gets smaller toward one side of the spectrum or the other side of the spectrum, and that's going to affect how you adjust this, how you adjust the focus. Okay, so just keeping that in mind, and here's our this is a program written in processing that starts the first of our two user interfaces. Okay, this is the Calibrometer 2020 program, and you can see up here it says connected on COM3. So when we opened this up, it immediately connected. There are a number of things that the spectrometer will write to the user interface, and one of those is the serial number. You can see this says down here serial 0011, and this is something that we can delete that and put in whatever we want. How about we just call it Jack for right now? We can put in any 4-character serial number, and we write that to the serial, and now the spectrometer is called Jack. Okay, so if we unplug the spectrometer and we hit the connect button, I guess I should pull that down. I should have made this a little larger. You can see it says no response because it's unplugged. What I'm going to do now is plug it back in and hit the connect button again, and we'll see that it is going to come up connected on COM3 with the serial number still saying Jack. Okay, so the serial number is something that is saved in non-volatile memory so that it doesn't go away when you unplug the instrument, when you power down the instrument. There are a couple of other things that are put into EEPROM, the non-volatile memory. One is the amplifier value and the other is the offset. Let's take a look at what happens when we hit the run button. Okay, so our first spectrum of the day comes out looking kind of crappy, but that's life. Okay, so let's just go up here and we'll click on file 1 and it will quit being there. Alright, so right now we're getting pretty decent looking spectrum. I would like to point out the effect of changing the values here on the amp and the offset. It's now at 180 and 125, and these are numbers that I found experimentally to be appropriate. So let's see what happens when we change this number. Let's call it 100, and we're going to write that to the amplifier, and we're going to start the run again, and you'll see now that the new spectrum is less intense than the spectrum we acquired just a second ago, and that is because there's hardware amplification built into the spectrometer, and the amplification value is determined by this number here. Okay, there's also an offset. You can see that this is shifted up as well as being smaller. We can change that offset value, let's say 100, write that to the amp, and we'll start another run. So now you see we have this smaller spectrum from decreasing the amp value, and we've shifted it down from where it was at 125. So what we need to do is go back to 125, 150, make it a little closer to where we want it to be, and let's get rid of the blue file there, the original one. That's the correct response, that one. Alright, and my guess is that we're off the bottom with this one, so let's start this one. And I guess I should say that every time we run a new spectrum, the current spectrum is shown in black. Okay, so that should be our current spectrum. We should have 3 of them up there. I don't know where it went. What happened to? I don't know what happened to. It's not looking like there's a lot of difference. Anyway, if we go back to 180 and 125, write it to the amplifier, and start again, then you see we get our optimized spectrum. We get as high a peak as we can, and our baseline is about 0. We want the baseline to be a little bit above 0, as little above 0 as we can get away with. We want to make sure we're not losing information by having the offset too high. Alright, so that is that. What else do we have here? We have a spectrometer name that we can name the spectrometer. We have some values down here. We have the integration time. That's an important factor for spectral acquisition. If we have it at 2, we get this value, or this spectrum. If we set it to 1, we're going to acquire spectra on a smaller time scale, and that's going to mean less intensity. Okay, so with 2 millisecond integration time, we got the brown spectrum. 1 millisecond integration time, we have the black spectrum. Okay, you can't just go to crazy town here. Let's put it up to 6 and see what happens with the 6 millisecond integration time. If we run that, what you'll see is that we screw up our data on your high peaks, and what we're doing is we're saturating the detector. The detector can read up to 4095 counts, which is, well, it's definitely maxed out. This isn't going all the way to 4095 because of the amplification not being quite high enough. Anyway, if you see flattened spectral peaks like this, you'll know that your integration time is too high. Alright, so let's back that down to 2, and we should be good. Loops over here tells the spectrometer how many spectra to acquire. Alright, so set to 4 like it is, we acquire 4 spectra, and for each pixel you average the values, the intensity values for each of those 4 pixels together and report the number. The spectrometer does that in the hardware. Over here it says data averaging. That is for spectral data smoothing. Okay, so if we make a larger number, if we say 2 instead of 1, then every other pixel, well, you'll average every 2 pixels together, and you'll have half as many data points, but they'll be more reliable. Min and max down here have to do with the displayed spectrum, and I haven't quite worked out how I want that to be, so we'll be discussing that in a later video. Let's say we want to do a bunch of spectra with a 1 millisecond integration, and we want to have let's say 8 loops, so we'll get more data averaged in there, and we want to do this a bunch of times, and we don't want to have to change the numbers each time. What we can do is we can write a file by clicking the set parameters button there. Call this setup w3. Okay, so we'll save that in there, and next time we go to do this, let's go run this thing again, and we're going to want to get back to the values we had down here. So let's read those parameters in, set up W3, and now you see it says the 1 millisecond integration time, 8 loops, and all the values in this box are saved in that file. If you want to forever change the values that show up when wake up the thing, you go to cal setup data, and you can save over that. Alright, so if we save over that, then the next time you start the spectrometer, it will have the values you put in there. Alright, so let's go to the next topic. We're going to work on the wavelength calibration. So what we need to do is have our compact fluorescent lamp spectrum on the display. We want to have a single file in the view, and what we want to do is we want to select that peak there. So we're going to click on that. That should be at 404.6 nanometers. And now we're going to hit the peak pick button. You'll see it says pixel 10. When we hit peak pick, it's going to change. It's going to say that the highest intensity pixel in this area is at 746 pixel number. Okay, going to the next peak, that should be at 435.8. We're going to peak pick that one. We're going to come over here and get the large one here, large one of those two. That should be at 546.1. This guy over here should be at 611.6. And finally, this guy down there should be 631.1. So we're going to peak pick all those. We're going to have values in here, and I've just picked all of them, but we don't need to pick all of them to do this. What we're going to do is we're going to select the ones that we want, and you don't have to select them all, but I'm going to. And once you have the ones that you want to use in the least squares refinement selected, you hit calculate. Alright, and now we should have the peaks in their appropriate positions. Okay, so over here, that's at 403.5. It should be at 404.6. You know what? Let's zoom in on this a little bit. we'll take those 2 peaks there. There's a zoom button up here, just off screen. And now we can see that that is right at 404.6, which is what it should be. The next one should be at 435.8, 435.2, 0.3, not too bad. Unzoom it. Yeah. Anyway, you can take a look at those and see where they are, and they should be okay. All right. Now that we have the values selected, we want to write the parameters into the memory of the spectrometer. And when we hit that button, that should happen. Okay. So next time we open this spectrometer, it should transmit the appropriate values to the user interface, and when we hit the run button, it should come up all calibrated. So this peak should be at 404.6. This one should be at 435.8. That one should be at 546.1. This one should be at 611 and some change. All right, so that's where we're at here. And let's see, is there anything else I wanted to tell you? Well, we still have some bugs to work out, but now I want to make sure I get this thing online, and we will squish bugs as we find them. All right, thanks a lot for listening.